Hi everyone. In the last class, we discussed extensively about dependent voltage sources and dependent current sources. So in this class, I'll solve problems based on dependent sources, okay, and resistors. Because in the previous few lectures we were trying to find equivalent resistors for a complex network of resistive circuits. So now we will add dependent sources to it, and we already saw when we add independent sources how to analyze a resistive network with independent sources. So now we will go about analyzing resistive networks with dependent sources. I'll also explain here and there, briefly, about how some of the circuits are used in actual amplifiers. So first, consider the simplest dependent voltage source. It's a current dependent voltage source. Okay. So the voltage across the two terminals is dependent upon the current, and that is given by IR. Okay. Now this is nothing but a resistor. Okay. So this is actually an equivalent model of a resistor using a dependent voltage source. Or you can also say that a resistor is nothing but a dependent voltage source whose voltage depends upon the current flowing through the two terminals of the element. Okay. Similarly, I can model a resistance also using a voltage dependent current source, where V is the voltage across this and I is given by V upon R. This is also equivalent to a resistance because we know the current through the resistance is simply V upon R. So these are the two circuit models for dependent circuit models for resistors using dependent sources. So now I'll just take you through a set of problems. So the first one is, you have a resistance connected. So this is minus a V in, where V in is the voltage between the input to ground. So the potential at this node is V in. So this node voltage is minus a times V in. So the current across the resistance is simply V in minus a V in upon R. So V in into 1 plus a by R. So the equivalent resistance seen at this point is simply V in by I, which would be R by 1 plus a. So that's your equivalent resistance in this problem. So using a combination of a dependent voltage source, I could actually synthesize a lower value of resistance. I can divide the value of the resistance, okay, using a dependent voltage source. Now this effect we will later study. It's called Miller effect. Okay, we will later study. This is used for capacitances, but I've shown it for resistors here. The concept is very similar. So you are supposed to find the equivalent resistance of this circuit again. Okay. So same way, if you know the voltage across this, you simply have to find the current flowing through this. You can apply KCLs and KVLs, but first try using the concepts we know already, some ideas we know already. Now this is a current source and resistance in parallel, so you can use source transformation to represent this as a resistance and a voltage source in series. The value of this voltage is simply I into R. So in this case the current direction is downward. So the voltage, open circuit voltage at this point would simply be minus GR into V in. And the equivalent resistance is simply R. At this point when you find it, it is simply R. And then we have R at this point. So you are supposed to find equivalent resistance here. This is V in. Now this is a very simple circuit. It is now reduced to a very simple circuit to solve. You need to find the current through this. Now these two resistors are in series. You can replace it by a single resistance of value 2R. So the current is simply V in minus GR V in upon 2R. So the equivalent resistance V in upon I is simply 2R by 1 plus GR. Okay. So this is also a very similar circuit. If you see in the previous if you compare it to the previous circuit shown here, it's a very similar you get the final result looks somewhat similar. The resistance is getting divided by a factor, your R is getting divided, but there is a small difference here. Again, this is another application of Miller effect, okay, with dependent sources, with voltage dependent current source. Now we'll go to another problem here. So assume a 1 volt source across a resistance. So this problem we want to cover how do you analyze it in the presence of independent voltage sources. So you're supposed to find where I is the current here, the equivalent resistance at this point. Now how do you go about analyzing this? So you are supposed to find the total current, let's call it IT, and this voltage across this is say VT, and I'm supposed to find IT. So VT is simply I into R because it's entirely across the resistance R here. The only thing is I need to find IT in terms of I, then I can get a result purely in terms of R, or the parameters given in the circuit. So your IT, to find IT, first this node voltage is VT. I'll assume this is ground, it makes analysis easier. If this is VT, 3 IR, VT is simply IR. So this node voltage is I into R, and there is a voltage drop of 3 into IR. It's a current dependent voltage source. So this node is at I into R, the potential here. You drop 3R across it, so this becomes minus 2 IR. Now when you are given a circuit with dependent and independent, you should first short the dependent sources, voltage sources. You have to make it 0, which is equivalent to shorting it. So that shorts out the resistance too. Okay. So this resistance has no effect. Now the potential at this point, we know that this is IR is the voltage potential at this point. Now if you subtract 3 IR out of it, you get minus 2 IR. The potential at this point is minus 2 IR with respect to ground. So the voltage across this resistance, this is all the same point. This is the same point. The voltage across the resistance here is minus 2 IR. So you have a current of value minus 2I flowing in this direction, or I can reverse the direction and say a current 2I flowing in the upward direction, in the opposite direction. Okay. So now if you look at this resistance, the current flowing through this resistance here is you have a voltage of 3 IR across this. So you have a current of 3I flowing in this direction. Okay. Now I need to find what is the current flowing in this guy. Then I'll apply KCL at this node, at the input node. Okay. So my goal is to find what is the current flowing to the resistance, the dependent current source. So now the current entering this node, I'll consider this node. Let me just redraw that part. The current entering this node is 2I. The current entering here is 3I from the resistor. So the current leaving here would be 5I. Apply a simple KCL at this node. The current going upward is simply 5I. So now we'll go back to the input point at this point here. The input point, through the resistor you have a current I flowing downward, and into the another resistor you have a current of 3I flowing here, and from the dependent source you have a current 5I entering. So what will be the current here? The terminal current, it will be I leaving this node. But we know I've said the current flowing in this direction is IT, so IT is simply equal to minus I. So we know VT is IR, and VT by IT is your equivalent resistance, which is simply IR upon minus I, which is minus R. So you actually got a negative resistance. So you should remember that in reality you don't find negative resistances. You need to do something extra, something additional to get a negative resistance. You don't normally find resistors which are of negative value. A negative resistance means that you are able to deliver power. Resistor is able to deliver power. So for example, if I connect a voltage source, say a 1 volt source across a resistance of value R, we know that resistance absorbs power and the voltage source delivers power. Current is flowing from the voltage source into the resistance. But if the resistance is negative, you have a negative resistance, then current will flow into the voltage source. It will flow into the voltage source. Rather, the resistance will now deliver power. Okay, and the voltage source will absorb the power. So this negative resistance can be synthesized, can be realized using active elements. It is used in oscillators, circuits like oscillators, and even in high-speed comparators. We will see probably in the later part of the course when we discuss about oscillators, or probably in a different course, I'll cover about negative resistances. But it is synthesizable. It is practical. We can generate it realize a negative resistance using amplifiers. Okay, I'll move on to another problem. So this class is entirely on solving problems. I'm not covering any ideas or concepts here. So you need to find equivalent resistance at this point. So if you have been seeing what I've done so far in the analysis, I have, for whenever there was an independent source, I made the independent sources 0, but dependent sources I've left them as it is. Okay, dependent sources I've retained them as it is and then kept them and found the analysis, and then did the analysis to find the equivalent resistances. Okay. So in this circuit, it's given V in is the input voltage. You need to find what is I. Simply V in upon I will be your equivalent resistance. So all you need to do is find I in terms of V in. So the voltage at this point, if this is V in here, the voltage at this point is simply the voltage. This is not R. This is A. The voltage at this point is simply V in upon A. Okay. So the current here through the resistor is simply given by V in upon AR. So this current is same as the current here. It's a current dependent current source. The current value is dependent upon the current flowing here, current at this point. So this value is also V in by AR. So V in by I is simply A into R. Okay. So here I have designed a circuit which can actually multiply the resistance by a factor A using a combination of two dependent sources. Now we will solve another problem. So say for you have a complex network of circuit consisting of dependent sources, independent sources and resistance. You find the equivalent resistance at this point, and then I connect a resistance here R. The equivalent resistance at this point will simply be, let me call it R dash, will simply be R parallel R equivalent. Okay, so I can simply add a resistance in parallel here. It would simply, the equivalent resistance will simply be parallel at this point. If I add a resistance, it will simply be in parallel with R and R equivalent. R parallel R equivalent will be the resistance. Okay, so these are all very, it's obvious if you have done a basic course on circuits, but for those of you who are learning for the first time, I'm just giving those points out. We'll analyze another circuit. So you are supposed to find the equivalent resistance at this point, okay, where I is the current through this resistor. So first, this is a dependent current source. So we make the dependent current source go to 0, independent current source go to 0. So you open these 2 points. So your R equivalent will simply be Vi by Ni. Your goal is now to find what is the value of Ni, because that is the current flowing here. That's simply Ni, and your goal is to find what is I in terms of Vi. So I from this circuit at this point is simply N times Vi upon R. So if I replace that here, I would get Vi by N square into Vi by R. R equivalent is simply R by N square. Okay, equivalent resistance seen at this point is actually R by N square. So for those of you who have studied transformers or have taken a basic course on electrical circuits, would know that this is a model of a 1:n turn transformer. Okay, this model, the circuit here using our dependent sources, I've modeled the 1:n turn transformer. So if I apply a load resistance of value R, the input resistance would be the equivalent resistance seen at the input at the primary winding will be R by N square. This is a well-known result in transformers. I've just obtained the same result but using dependent sources. Okay, this is mathematical model for a transformer. I mean, what I've shown here is a mathematical model for a transformer using dependent sources. So same way, if we can also model a n:1 turn transformer. So this is V in. So you're supposed to find the equivalent resistance at this point. So again, you need to find what is the value of the current here. So the value of I in this equation is simply V in by NR. So the current flowing here, I dash, I'm going to call that as IT, will simply be equal to, it will be, let me call it as IT, will simply be I by N, which is V in by N square R. So your R equivalent is simply V in upon IT, which is N square into R. Okay. So again, as I said, this is a model, circuit equivalent model for n:1 turn transformer, ideal transformer. I'll analyze a few more circuits. So you're supposed to find the equivalent resistance at this point. This circuit consists of a current dependent current source, okay, which actually multiplies the current flowing through the resistor or the input by a factor beta at this point. So how do you find? So first assume that test voltage Vt is applied here with respect to ground. You need to find Vt upon I. So in this loop, if I apply KVL in this loop, the voltage drop across R is simply I into R, and the voltage drop across the other resistance here can be found by knowing the current through this. So the current entering here is I. The current entering at this node is beta I, because that's a dependent source. So the current entering this resistance at this point is beta plus 1 into I. So this voltage drop will be beta plus 1 I into R. So your Vt, the total voltage at this point, the input point, is drop across this plus the drop across this resistance, which is IR plus beta plus 1 IR. So your Vt becomes I into R into beta plus 2. Okay. So your equivalent resistance is simply R into beta plus 2. Again, this is what happens in what we call bipolar junction transistors. So again, this circuit model is just to introduce you to that concept. Later when we do BJTs, you will be able to connect the dots. So here I'll take two interesting circuits. So you're supposed to find an equivalent circuit where I is the current through this. So in the beginning of the lecture, I said a resistor can be modeled as a dependent voltage source, a current dependent voltage source in this fashion, but here it is minus. There is a negative sign here. Instead of IR, it is actually minus IR, So I can simply replace this with a negative resistance of value minus R. So if I have a resistance R and you put it in series with minus R, the net resistance, the equivalent resistance would be 0, right? It's a short circuit. Between these 2 points, it's a short circuit. Okay, so IR plus IR is 0. So the equivalent resistance would simply be 0. So even if you apply a finite voltage, the current drawn will be very high. Okay, so that's why the equivalent resistance would be 0. Now I can also see that these two are in series. R plus minus R is 0. So similarly, I'll take another circuit which is R here, and let's model it as a current source of value Vin upon R. So Vin is the voltage across this. You're supposed to find, or the voltage across this resistance is Vin, which is same as this. You're supposed to find the equivalent resistance at this point. So again, as we discussed in the beginning of the class, if you apply a voltage Vin, if a current flows into the voltage source, then it's a negative resistance of value minus R. Okay, then if I put R and minus R in parallel, you would get a infinite resistance. The equivalent resistance would be infinity, because it is R into minus R by R minus R, which is infinity. You can also intuitively see that if I apply a test voltage Vt and try measuring the current It through this, I put a minus resistance of minus R. So we have a current of Vt by R flowing in this direction. You have a current of Vt by R flowing in the opposite direction. So if you apply KCL at this node, you have a current Vt by R leaving here, Vt by R entering here. So the current at this point will simply be 0. So as far as this circuit is concerned, as far as Vt is concerned, it looks like as though this circuit is drawing no current. It's drawing It is 0. It's drawing 0 current here. Okay, so if you apply a finite voltage and you are drawing a 0 current out of it, then the equivalent resistance is simply infinity. You can also see this resistor is absorbing power and this resistor is delivering power. The power absorbed by this resistor is exactly equal to the power delivered by this resistor. So this voltage source doesn't have to deliver any power. Neither it needs to deliver nor it needs to absorb. Okay, every power that this resistor is absorbing is purely provided by this resistance. So this doesn't need an external excitation to provide or absorb power. So it's like this. You have a resistance and a resistance of value minus R. They can sustain themselves. Okay, by if you apply some voltage and leave it, or this, in this case, a negative resistance can actually sustain current in this loop. Okay, yeah. So these are the problems I wanted to discuss. So probably few more problems we'll discuss in the next class, but the basic points to consider is that when you have dependent sources, you don't have to make them 0. Only independent sources have to be made to 0 when you're finding equivalent resistances. Okay, and we have seen some various applications of dependent sources to model resistors, negative resistors, resistance multipliers, resistance dividers, and even in amplifiers in the last class. Okay, so I'll stop at this point and we'll continue in the next class about capacitors.